Hello everyone and welcome back. In today's video, I'm going to be talking to you about something which is called an improper integral and how to calculate that. Okay, so to demonstrate what an improper integral looks like and how to calculate one, let's consider the following example. We're asked to calculate the integral from 1 to infinity of 1 over x to the 7th power dx. Now, when you're looking at an improper integral like this, where one of the limits of integration is positive or negative infinity, graphically you can think about it this way. We remember that the definite integral captured the area under a curve. And the limits of integration told us the first and final x values for which that net area was being measured. But the graph of the function 1 over x to the 7th extends infinitely to the right. And what an improper integral allows us to do is to calculate net areas for the entire right portion of the graph, all the way from 1 up to infinity. Just keep calculating net area off into the horizon for as far as the graph goes. The actual process of calculating an improper integral is not much different than what we've done up to this point. To start with the improper integral, then you can start it just the same way you would any other definite integral, for example, using fundamental theorem of calculus and finding an antiderivative of your integrand. So integrating x to the negative 7 dx, I use power rule, so I get negative 1/7 x to the minus 6 plus c. And then in a definite integral, the next thing that we would do is we would take this antiderivative and we would plug the limits into that antiderivative and subtract. The only issue here now is that you cannot, technically speaking, plug in infinity, right? So instead, what we're going to do is instead of plugging in infinity, we're going to plug in a placeholder quantity. We're going to plug in a placeholder b for infinity. And I'll say, okay, negative 1/7 b to the power minus 6 minus negative, so plus 1/7 1 to the power 1/6. And then once that placeholder b has been plugged in for the upper limit, and once 1 has been plugged in for the lower limit, and I've subtracted those two results, now I'm going to simply let my placeholder b approach infinity. And if you wanted to be really careful, you could express it as a limit. Let b approach infinity in a limit. So let's think about what happens to this quantity as b becomes very, very large. If I raise a very large number to a negative exponent, then I am essentially dividing by an extremely large number. So because of that negative exponent, as b goes to infinity, b to the minus 6 approaches 0. And as a result, this first term vanishes, and all that is left behind is the value 1/7. And this would be my final answer. Now we've just done an example where the upper limit of integration is positive infinity, and the graph of your function is extending infinitely to the right. Let's do another example where the lower limit of integration is negative infinity, and your graph is extending infinitely to the left. Here's the graph of the function 1 over x to the 6th power on the left side. And we're just letting it extend infinitely toward negative infinity, and we are calculating the net area between negative 4 all the way to negative infinity. Once again, the game begins the same way that it always does, by finding an antiderivative of your function. And so using power rule again, we have negative 1 over 5, x to the negative fifth power. And I'm going to plug in an upper limit of negative 4, and I'm going to quote unquote plug in negative infinity, but that doesn't quite make sense. So instead, I'm going to plug in a placeholder value of a as my lower limit. And this gives me negative 1/5 minus 4 to the power minus 5 minus negative 1/5 a to the power minus 5. And then I'm going to let that a approach negative infinity in a limit. Now, once again, if I do that, and if I take a very large negative quantity and I raise it to a negative exponent, then that negative exponent pushes the number into the denominator of a fraction, and that causes that result to become very, very small. And it will approach 0 as a gets larger and larger. So in total, this term in the back vanishes, and the only non-zero term that is left in the calculation is this one in front, and this would be the value of this definite integral. Now, in both of these cases, we've gotten answers that are finite. And that's a little bit surprising, isn't it? That we were able to, in some sense, calculate the area of an infinite region, extending infinitely to the right or infinitely to the left, and we were able to get a finite value from that calculation. This has happened in these two cases, but it doesn't always occur that you get a finite number from a calculation like this. To give you an example of a situation like that, let's consider the integral of 1 over the square root of x dx, where x is going from 3 to positive infinity. I'm going to go ahead the usual way, and I'm going to start by finding the antiderivative of this integrand, which I can think of as x to the power minus 1/2. If I apply power rule to that, increase the power by 1 unit, and then divide by that increased power, I can then evaluate as x goes from 3 up to a placeholder value that I will just call b. And if I plug that in, and I get 2 times b to the power 1/2 minus 2 times 3 to the power 1/2. And then I'm going to let b approach infinity. But what happens when you take a very large number and you take the square root of that very large number? The square root of an extremely large number is still very, very big. And as b approaches infinity, the square root of b will approach infinity as well. Now, if you have something that's infinite and you subtract a tiny number from that, the result of that is still going to be infinite. So from this we have infinity as the result of our calculation of this improper integral. So we have a little bit of language that is used to distinguish this situation where we got an infinite result from these two situations where we got a finite result. We say that an improper integral converges if its value is finite. And we say that the integral diverges if its value is not a finite number, if it does not converge. So to apply that language to these examples, I would say that this integral diverges. Why? Because its value is infinite. I would say that this integral converges. Why? Because its value was finite. I would say that this integral converges, once again, because its value is finite. Now for our final example, I just want to show you that it is possible to have both the upper limit and the lower limit be infinite. And to that end, let's consider this situation. I'm asked to integrate from negative infinity to positive infinity of this function right here, 1 over 1 plus x squared. So we are essentially trying to calculate all the net area for this function, all the way from the left side, all the way to the right side, the complete total of all the net area between this graph and the x-axis. So I'm going to start, as always, by finding an antiderivative, which for this integrand, we have a special formula. The antiderivative is arctan. And I'm going to plug in a lower limit called a, and I'm going to plug in an upper limit called b, just as placeholders. And then I'm going to use limits to allow that b value to become positive infinity, and I'm going to let that a value become negative infinity. So now the question becomes, what is the limit of arctan at these two extremes here? What does arctan become when you plug in values that are really, really big? And what does arctan become when you plug in values that are really, really small? You might remember the answer to that question from calculus or from trigonometry, but in case you don't, let's look at the graph of arctan of x for some insight. So here in red is the curve of arctan of x, and if I wanted the limit as x goes to positive infinity, I would be investigating what the graph is doing on the right-hand side. Now, as we approach the right-hand side of this picture, the red graph is leveling off at a y value of exactly pi over 2 units. So pi over 2 would be the limit of arctan as the inputs approach positive infinity. Let's go to the graph's left side to figure out what is happening with this limit as a approaches minus infinity. And due to the symmetry that is in this picture, you might be able to predict it. If the right half is approaching positive pi over 2, the left half is just approaching negative pi over 2. So that is the limit of this term in the back, pi over 2 minus negative pi over 2. So in total, we have two copies of half of pi. In total, we just have pi. And so pi is the exact value of all of the net area between this function and the x-axis on the function's entire domain.